Physics वाले में रह रहा था या अपने जब जैसे कि मैंने कॉल बाहर नहीं चलाई अंदर चलाई ओके इसमें फाउंड लगा दिया
Hello. Should we start? Yeah. Turns out I still can't get my microphone this to work. So maybe we should try it next time for longer. So we're trying to get this thing to work every time. It's this speaker, it's this wireless mic system. Okay. But it's tricky. Alright, let's start. So today we'll continue to see greedy algorithms. Okay, so last time, if you remember, we saw longest increasing subsequence. So this was a use of dynamic programming. And we also saw this example of coin change. Okay, so we saw that there's a natural dynamic programming way to do it, but it can be done much faster using a very simple greedy approach. But the greedy approach doesn't always work. Okay, so this is what we saw last time. And a related problem to this, which we'll also explore in the homeworks, is what's called a knapsack problem. Okay, so it's kind of a generalization of this coin change problem. So where it's not the number of coins that you want to minimize, it's some weighted sum of the number of coins that you want to minimize. Okay. So that's that. And we also saw this example of creating project pairs. Okay, so we said this was our first introduction to some graph problem, where we said that you wanted to just create as many pairs as possible. Okay. And I'll just recap that in a bit. But so this is what we did last class. So have you guys all gotten started on the homework? Hopefully, yeah. So it's due 1 week from now. Okay, so quick recap of greedy. So the idea behind greedy algorithms is that at every step, you try to pick the best option that's available to you right now. Okay, so you don't try to go back and change the solution that you have. And you just build up a solution iteratively and always make locally the best moves. Okay, so that's greedy. And as we said, it doesn't usually work, but often it gives some insight into what the right method should be. So, and we also saw sometimes it almost works. And so this is the example we saw last time. So we had a bunch of people. Each person gives a list of people whom they are compatible with, and you want to form as many compatible pairs as possible. So, and we said that there's this very simple greedy algorithm, which is pair two arbitrary people who are willing to be paired. And remove them from this graph and just recurse. Okay. So do you have a question? No. So, and we said that this algorithm is what we call a two approximation, in the sense that if the optimum number of pairs, so using any possible algorithm, potentially exponential time algorithm, is k, then we said that this very simple algorithm produces at least k over 2 pairs. So it's not terribly bad. Okay. So what I want to do today is, in some sense, talk more about how you reason about greedy algorithms. Okay. And greedy algorithms are one of the few things where it's easy to come up with the algorithm, but it's hard to reason about it. Okay. So usually coming up with an algorithm is itself tricky. But in these cases, it's usually easy to come up with the algorithm, but it's hard to prove that it actually is correct or reasonable. Okay, so the example that we are going to see today, the first one is what is called scheduling jobs. So what I will call scheduling jobs. Okay, so what is the problem here? The problem is the following. Okay, so you have a bunch of jobs. So let's think of them as some computing tasks or something like this. So you have J1, J2 up to Jn. And each job comes with a processing time. Okay, so J1 has processing time P1, J2 has processing time P2, and so on. This one has processing time Pn. Okay. Now, the question is, so now the goal is to find a scheduling of these jobs. The goal is to schedule these jobs on one machine. On one machine. So what does this mean? So you first, so let's say this is the time axis. So this is what the machine is doing. So, and this is time equals 0. So what you want to do is, first you want to pick some job to do. So maybe this is J2, then you do some J4, then maybe you want to come back and do J1, and so on. So a schedule is basically a permutation of the jobs. And this is the order in which you want to actually execute them. And the goal, the objective rather, is to find a schedule that minimizes the sum of the completion times. Okay. So what does completion time mean? So let's look at let's say this is the schedule. Okay. So the completion time, which I'll call C2. So Cj denotes the completion time of job j. Okay. So C2 is basically the length of this is P2. Right. So the completion time of job 2 is P2. Okay. So what is the completion time of job 1?
P2 plus P4 plus P1.
Yeah, so you get the idea, right? So this is P4, this is P1. So C1 is actually P2 plus P4 plus P1. Okay. And maybe 3 was done here. So C3 will be P1 plus P2 plus P3 plus P4. Okay. So that's how you compute these. And the goal is to minimize the sum of these completion time. Okay, so which is sum over I Ci. Okay. So minimize this one. Okay, so this is our goal. So you want to minimize the sum of these. So question is, how do you schedule these jobs so that you actually minimize this completion time? So let's take a simple example and see what's going on. Okay? So this is how you usually try to come up with algorithm. So first you let's say take a simple example. So let's say we have jobs J1, J2, J3, and this one has processing time 3, this one has processing time 1, and this one has processing time 4. Okay. Now, okay, so let's take two possible schedules, right? So let's take the simplest one where you first schedule J1, then schedule J2, then J3. Okay. So what's the cost of this? So we are saying that J1 takes 3, J2 takes 1, and J3 takes 4. Okay. So note that the total length of the schedule is always the same, it's just the sum of the PIs. Okay. So, but the objective is slightly different. So now we have C1 equals 3, C2 equals 4, and C3 equals 8. So now what happens if you schedule, let's say J2 first, and now you have J1, let's say, and then you have J3. So in this case, you're doing this one guy first, and then you have 3, and you have 4. So now note that the completion times, the first complete C1 is 4, C2 though is pretty small, it's just 1, okay, and C3 is still the same. Okay. So does it give you a hint of, suppose I tell you which, suppose I ask you what jobs do you want to do first? Okay. So any ideas? What would you, like this objective function, So what would it prefer? I mean, in the sense, if you want to minimize this objective function, what jobs would you do first?
418.
You do the short jobs first, right? Because basically they will contribute less to this completion time of the other guys. Okay, so this is a very simple example. So you can convince yourself by playing with a few examples that it helps to do the short jobs first, because in some sense the completion times for the rest will actually, in general, will be small. Yeah.
What is the physical implication of this parameter? Because if you see the sum of the total time is same.
Yeah.
Why do we need to wait at each stage and see how does that?
Oh, so it depends. So there are various objectives you can think of for scheduling. So we'll see the one that you are saying also in a bit. But this could be, for instance, bunch of people submit their jobs, and their unhappiness level is when they finish their job. Okay. So let's say they are more. I mean, they want their job to finish first, right? Early. Okay. And and your goal as a system designer could be to minimize the average unhappiness. Okay. So average is like the sum, basically, right? So the completion time is basically the price you're paying to some particular user, let's say. So this could also actually be some payoff type thing. So maybe the system designer has to, if you make somebody pay a long time, wait a long time, then maybe you have to pay them something.
Even in cases like this C1 or C2 are a part of input of some other task, then it is better to finish them off early than holding them because
yeah. So that's the general motivation, but I guess he's asking why the sum. Okay, so why is the sum of this completion time important? Okay, so what I was saying is, so if different people submitted jobs, then each one cares only about his job, not about when the machine is finishing up everything, right? So as a system designer, you care about that, but each person individually cares about his own job. Okay, so those are the kind of places where people use this sort of an object. Yeah, by the way, this is a good question. Every time you try to optimize something, you should ask yourself, why am I trying to do this? Okay, so it's useful to do. So in this case, there is some motivation for this. And what we said the algorithm was basically do the short jobs first, right? Small jobs first. Okay. And formally, what is the algorithm then?
Sort.
Yeah, you just sort the jobs by PI. So algorithm. According to PI and schedule in increasing order. Okay, so this is the very simple algorithm. As I said, greedy algorithms are usually very simple. Okay, so that's a nice thing about it. And I claim that this is actually optimal. Okay, so let's try to prove that this is actually optimal. So let's see. So how do we prove this? So this is again something that we saw last time. So this is how you generally prove the correctness of a greedy algorithm. Okay, so you say that, okay, my algorithm does something, consider the optimal schedule, and I'm going to show that the optimal schedule that my algorithm does at least as well. Okay, so this is what we were also seeing last time. Okay, so we'll show this for this algorithm. Okay, so I'm saying that consider any feasible schedule, and I'm going to show that the sum of completion times is bigger than that of what greedy does. So this is the claim that we're going to show. So any idea how to go about? So I'm saying consider any schedule, right? So let's say I look at j some pi 1, j pi 2, j pi of n, where pi is some permutation. So note that any schedule is just something like this. Okay, so pi is a permutation of the numbers 1 through n, and I'm just saying this is any possible schedule is something like this. Okay, so and this has some p pi 1. So this is the job that's scheduled first. This is p pi 2, and so on. So how would you argue that the sum of completion times here is at least as big as the sum of completion times in greedy? Yeah. Yeah.
So could we approach it as a proof by contradiction?
Okay.
Let's say we have the optimal one, and
Mhm.
let's say that it's greedy.
Okay.
We could say if you switch any arbitrary pair of numbers, we could prove that that increases the value.
Yeah, so this is one way of proving things. So what he wants to do is basically say that, okay, so you take the optimal schedule, and he wants to show that this has to have these PIs in increasing order. Okay. And he's saying that, okay, if they are not in increasing order, swap two of them. Like they have to be two consecutive guys who are not in increasing order. Now you swap them, okay, and this creates a better schedule. Okay, so this is one way of showing this. Okay. So I'm going to show an even simpler one, which is basically, so let's look at, so what is the sum of the completion times, right? So it's, once you know this permutation, this sum is pretty clear, right? So it's this one plus this time plus this time and so on, okay, until n, okay, and yeah, so what I want to claim is that if you look in this order of completion, okay, and if you look at the, let's say the kth completion time, so what I mean is completion time of kth job in this order, okay, so in the above order, okay, so which is this pi order, okay, so this order given by pi 1, pi 2, so on, right? So in this order, so this is basically p pi 1 plus p pi 2 to p pi k. So note that this is just the sum of k different processing times. Okay. So just because and so by definition this is bigger than or equal to the sum of the k smallest processing times. Okay. So I mean, so you have a bunch of numbers, you pick any k of them and sum them up. That sum is going to be bigger than or equal to the sum of the smallest k numbers, right? Just by definition. Okay, so this is bigger than or equal to sum of the k smallest number. Okay. But this is exactly the price that greedy is paying. Okay. So for greedy to complete the kth job, it's just paying the price of the sum of the k smallest things. Okay. So in particular for the kth job you have this, and in general you have this. Okay. So you have this for every k. Okay. So this is true for all k. And and that's it. Okay. So this is why the sum of completion times is bigger than or equal to what it is for greedy. Okay. So is the argument clear? So I'm just saying, just look in the order of completion in this order. The price you're paying is at least what greedy is paying for the kth job, and that's it. So what he said is also a good way of
So is this a robust enough proof for our purposes to show?
Because I guess you just have to write down some of the things I said in words.
Yeah.
Yeah.
Can you just explain what is J of pi of
So pi is any permutation. Okay, so think of it as, so you have numbers from 1 through n, 1, 2, 3 up to n. So pi could be, think of pi as an array. Okay, so pi is some array which is maybe n2, n minus 1, 1, something like this. Okay, so this is just a permutation of these numbers 1 through n. Okay. And pi of I is the ith number in this index, in this permutation. Okay. So this is just a convenient notation. So I want to say that consider any ordering of these jobs, right? So mathematically the way to say this is to say consider any permutation and look at that order. Okay. So that's fine. Okay, any other questions? Yeah.
How come is this greedy? Because we said in greedy, we will try to solve the first biggest chunk of the problem. But here we have to sort it, consider, and while solving it,
We are solving the smallest ones first. Okay, so we are scheduling the smallest jobs first. Okay, so that's why. So was that the question? We are not doing the big jobs first. We are doing the small ones first.
yeah. So when we sort it, when we sort the array, that time we will consider all the elements inside the array, not just the some part of the problem and pick it and solve it.
Yeah.
So that's what we define it as greedy. To take the
You sort it globally. Yes.
So when we define greedy, we said that we don't consider all the elements globally. We just one example. We said we'll take the first biggest one which can be. So we don't really consider all the possibilities.
Oh, I see. So you are saying that this is it's not an incremental thing. So one way to view this as an incremental thing is to say that I do the smallest job first. Then I look at the leftover jobs, I solve the smallest of those guys and so on.
Okay, it comes after this one.
No. So I'm just saying one way to think about this sorting thing is to just say I'll do the smallest job first, then I'll do the next smallest among the remaining and so on. Okay, so that's why it's greedy. So you're always doing the best job, the easiest job you can. Okay, so in that sense it's greedy.
So the job at hand is finish as many jobs as possible in the least possible time.
Yeah, so that's the goal.
So that's how so the biggest challenge is the number of jobs you finish.
Yes.
That's how it's
Yeah. Okay. So is this reasoning clear? So let's.
So why is that not n? Like why is that k? That statement like.
So I want to show this for every k. Okay. Because so the value of this objective is sum over k of this completion time of the kth job.
But total number of terms are n.
Total number of terms are n. Yes. So I am showing this for every k. So it's also valid for the sum.
For total sum.
K could be n.
Yeah. So you can think of k going from 1 through n. For each term, the price you are paying is bigger than or equal to the price that greedy is paying. Okay. So overall, the sum you pay is bigger than or equal to the sum that greedy pays. Okay. So good. If there are no other questions, let's go to this other thing. I wanted to just do one more example. So this is one of the standard examples that everybody does when it comes to greedy algorithm. So let's just, I guess people should be aware of this. Okay. So the problem here is, it's a simple one. This is one that many of you face. Okay. So you have one semester. You want to take as many credits as possible. Right? So let's say, you're awesome. You can ace every course. You don't care about the number of courses. Okay. So you have a bunch of courses. You want to take as many of them, okay, as you can. The only constraint is you can't take courses whose timings overlap. Okay. So you're awesome, but you can't be in 2 classes at the same time. Okay. So that's the only restriction. So let's do this. Okay. And the question is how you do this. Okay. So let's see. So formally, what is the problem? So you have a bunch of classes. Okay. Each class think of, okay, so I'm also assuming that every course you just meet only once, okay, so it's not like twice a week kind of thing, you just meet one slot, okay, one interval of time, okay. So you have the week ahead of you, so you have like Monday through Friday or something, Friday, and you have timings and so forth. Okay, so maybe the first class is Monday morning something to 10 a.m. to something 12 or something, and maybe you have something that some other course that starts from 11:30 and goes on till 1:15, something like this. So you have a bunch of courses which are given. Each course is just an interval, and maybe you have this. And maybe you have this super long course that just like goes on forever. Okay, so and so on. Okay, so you have a collection of intervals like this, and the objective, as I said, is you want to maximize the number of distinct courses that you take. Okay, so you want to. So mathematically, what's the problem? So you have a bunch of intervals. Okay, and each interval corresponds to one course, and you want to pick a collection of these intervals such that none of them overlap. Okay, so pick collection of intervals, largest collection of intervals. Such that no two of them overlap. So I don't know if this is visible, but so you don't want any two things to overlap. You want to pick the largest number. So how would we do this? So let's say, oh, okay. So I made this slide just for drawing this picture. Okay, so yeah, let me just draw this so that it's nicer. Okay, so you have this, and then you have a bunch of. This is the overall time. Okay, so this is time. 0. You have intervals that go like this, so on. You want to pick some collection, maybe this guy, this guy, this guy, and this is what you want to do. Alright, so now that we all have some practice in dynamic programming, okay, so again, let me write down the objective. Goal is to pick as many as possible. So now that we all know dynamic programming, so how would you try to go about this problem if you wanted to write, do some kind of a dynamic programming approach? Similar to what? The increasing.
You first order all your classes by some, the order of your choice.
Okay, arbitrary
By
order.
start time you can order.
Okay, so let's say we order by the starting time. Yeah.
So then, suppose you start off with the first class.
Okay.
If that's in your schedule, then you obviously can't. You need to eliminate the other classes that overlap and recurse on the classes that are there.
Okay. And what is the so how do you define the remaining?
So the start time should be greater than the finish time of this.
Yeah, exactly. Okay. So this is a feasible algorithm, right? So what he's saying is, I want to do dynamic programming, and I want to keep track of the starting time. Okay. So let's say I know how to solve this problem as long as the starting time is bigger than or equal to some t. Okay. So dynamic programming approach. Yeah. So the dynamic programming approach is keep track of optimum solution with start time bigger than or equal to t. Okay, so for any parameter t, you can think of starting time bigger than or equal to t, right? And now you can say, okay, so what is the optimal solution if I restrict you to start after this t? Okay. And if you solve this, then you can come up with this algorithm where you say that go through courses in increasing order of start time. And then you say that, okay, so I consider, let's say, some course I. Okay, so consider course I. Okay, and if I choose to do it, okay, so this has some starting time. So this is course I, this is some start I, and this is some end I. So let's just define course I has start time Si and end time Ei. Yeah.
Wouldn't you be doing this just for one day?
No. So I want to think of time as just being continuous.
That would make sense, right? Because you can have different start times on Monday and Tuesday. Because if you say they only meet once a week.
Yeah. So that's why, right? So this is where Monday starts. Maybe Monday ends over here. Or rather Tuesday starts over here, Wednesday starts over here, and so on.
You wouldn't have overlap between Monday and Tuesday.
Yes, you would not have. Just because one interval would be here, one interval would be here.
Right, so then each day is independent.
Yes, by definition.
Right.
I mean, yeah, because...
So then my question is, what we're talking about right now, wouldn't we be doing that separately for each day?
No, you can just think of doing this for the whole interval, right? Because you can just, they by default don't overlap. Like if you solve this, you don't have to solve this for every
Right,
day.
but would you have different options for each day, or are we just assuming that our options are the same for every day?
No, there are different ones. There could be different ones, right? In fact, there will be different ones. You can't have the same guy appearing twice, right? So every day there will be different options, but that's fine, right? So they won't overlap by definition. So the ones on Monday will be disjoint from the ones on Tuesday.
Right. So then I'm confused about why you're saying you're looking at it as just being this.
Oh, because you might as well. I mean.
Well, but why would you look at all of your options when they're independent each day?
Yes, so you could in principle, right, so in principle you could solve it for every day and just take the union of these. Okay. So that's also fine. So it's just that I am technically speaking allowing a course that starts on Monday evening and ends Tuesday morning. Okay, so that's the reason I'm just considering this as just one long interval. Okay, so if you really don't have classes that span different days, then you could just solve it on each day and just concatenate the solution. So yeah, that's a good point.
So we can logically segment each day in 24 hours.
Yes, if you want, or even finer if you want. So yeah. Okay. All right. So what I'm saying is, so you can think about it either way. Okay? So if you want, you can think about it as solving separately for each day. And okay, so what I want to do is, I'm looking at this course I, and if I choose to do it, okay, so if I choose to do it, then the most I can do is some course that starts after EI, right? So one option is to do, if we do course I, then the optimum number is 1 plus the value. Okay, so let's denote this by some name. Okay, so keep track of the optimum solution. Let's call it S of t. Okay, so S stands for the solution. Solution of t is the maximum number that you can do starting at t. Okay, so it's 1 plus S of EI. Okay, this is if we choose to do this course. and otherwise it's just otherwise basically S of SI. Right? If you choose not to do it, then you just start here and do, and you can maybe pick some other course that starts here. Okay. So
So basically saying that we should choose the minimum ending, like you choose courses that start earlier.
is that what?
So you should choose courses that end earlier.
Exactly. Okay, so that's what I was getting to. So, but yeah, so is this dynamic programming thing clear though? So now you can compute this S value starting from the right, and you basically and you can do dynamic programming. Okay, so and you can verify that this takes time roughly n squared. Okay, so this is for roughly the same reason all dynamic programming things take n squared. So you have to, yeah. So this is an exercise, easy exercise. You can verify. Okay, so now let's go to the observation that he was making, okay, which is the following. Okay, so what he observed is that this is S of t. Remember, S of t was a solution for courses that start. What's the maximum number of courses you can take starting at time t? So one thing that you can say is that. So, if you have two time periods t1 and t2, okay, and suppose t1 comes after t2, what can you say about the S of t values?
What is T1 and T2?
So, let's say I take two time steps, and here it's t1, t2 is here. Okay. So what can we say about the S values? Okay, so S of T2 is bigger than or equal to S of T1. And this is obvious, right? Because if I want you to start at T2, then I could basically do everything that I could have done after T1. Right? So this is just trivial. Okay. But this is a easy observation. And this motivates what you're saying essentially, that your goal when you're trying to do this should always be to try to end your last course as early as possible. Okay, so suppose I want to ask you, okay, so suppose I want to take as many courses as possible. Now I ask you to say, okay, what is the first course I should take? So what should be the first course that you take? You have a bunch of courses. Okay, so you have like something that ends, something that's like this, something that's like this, something that's maybe here, you have a short one, and maybe you have something else that ends over here.
The one with the shortest duration.
The one which is finishing first.
So yeah, so there are two reasonable answers that we got here. One is the course that is the shortest, and the course that ends first. Okay. So which one of these could be correct? Yeah, so it turns out the shortest is not really the good thing, because maybe you can have like a really short course that ends over here. Okay? And if you pick that to be your first course, then you just have options starting out here, right? Starting with this type. Okay? But if you had ended over here, then it's great. You have much more time to do. You have time to take other courses. Okay? So this is a simple observation. Okay, so you always want to pick the course that ends first. And having picked this, it's clear that you have to keep doing this, right? Because let's say you commit to picking this course. Then the next course that you pick, by the same reasoning, has to be among the ones remaining. You have to pick the one that ends first. So this is a natural greedy algorithm. And the greedy algorithm is, at each iteration, pick an available course with earliest end time. Okay. Okay, and this frees up time for you to, you can potentially take more courses like this. But now the question arises, so this is the problem always with greedy, okay, which is that maybe by committing to taking this course, maybe you lost some other better solution. Okay. So is that feasible? Is that possible in this case?
It's not possible because if you have a later end time, you will actually have a greater chance of losing more courses because their starting time must be less.
Yeah, so in this example, we are quite lucky. Okay, so it turns out this is not possible, and the reason is exactly this, in some sense. Okay, so but to do this formally, okay, so this is just slide I left. Okay, so and the greedy algorithm also we wrote here. Okay, so let's go to the correctness proof, and the proof is. So that's an intuitive argument, but usually the easiest way to prove these things is to do what I said. Consider any other solution, and you're going to show that what you are doing is better than that. Okay? So consider, Okay, so let's look at the optimum schedule. Okay, so let's say you have some optimal schedule, which is basically a collection of courses. Okay. So consider the largest collection of courses. And this is what I'm calling the opt schedule. Okay, so this is just some bunch of intervals like this, right? So this is again, this is the time. And let's say the optimum number that you can take is some k courses. Okay, so it's I want to claim that our greedy algorithm takes at least k courses. And why is that? So again, the proof will be by induction. Okay, so initially, okay, so when you haven't picked any courses, the greedy algorithm was picking the one that had the smallest completion time. Okay, so what that means is, by completion time I mean ending time. Okay, so the greedy algorithm was picking something that ended at most, earlier than this, right? Because this is one feasible course, this has some ending time. Okay. So in the greedy schedule, the course that you picked first has to end before this guy. Okay. So it could either be just here or it could be a little bit before. Okay. So what that means is, at this time, you have done as many courses as this optimum has done. Okay, and you ended only before this. Okay, or at most at this thing. Okay, which means that you are still free to take any of the courses that greedy can take, that optimum can take. Okay, so that's nice. Okay, so you have this. So that basically says that you can do this inductive argument, where you say that you look at the ending time of the jth course in optimum, and you claim that you have taken at least as many courses as optimum did. Okay. And this is by the same reasoning, because you have this inductively, and then you could have taken this course, but you potentially took something with a smaller ending time. But that's only better for you. Okay. So this is easy enough in access proof. And once you have this for all k, then you get that at the end you've taken at least as many courses as optimum. Okay? And that's what you want to show. So you could have note that this is one example where you could have picked a different schedule than optimum, or different set of courses. All you guarantee is that you pick at least as many. So that's why, well, so that shows the correctness. Yeah.
How do we write this? If we want to write this code.
So you write the inductive claim as clearly as possible. Okay. So so that is the key. So you have to write basically the inductive claim very clearly, and the proof, it's you write it out in words, right? So it could be a little bit off and so on, but the claim is the key. Okay. So you want to have the right claim. Presumably you write more than this. Okay. So, yeah.
I might just be confused, but it seems like if you had like a class that's really short, that's like 1 credit, but then you have.
Oh, we are not doing credits in this. Okay. So incorporating credits is trickier.
Okay.
So that will be. Yeah. So that's like a weighted version of this, right?
So all classes are the same amount of credits.
Yes.
Okay.
Yes. Okay. So that's why I switched from credits to number of courses when I wrote the objective. Okay, so that's yeah. So the credited version, you might want to think about it. It's more interesting than this. Okay, so there, then you can still do dynamic programming. Okay, but this greedy becomes harder. So yeah, maybe you want to think about the dynamic programming thing, and then you will. Okay, so any other questions? So there actually I don't know any way of doing it without doing dynamic programming. So yeah. Okay, so this is this and yeah, so this is basically all I want to say about greedy algorithms. So we'll encounter more of them during the course. Okay, so in particular, what's called spanning tree that we'll do maybe next week or the week after that. Okay, so we'll encounter these. So today I want to continue with what's called local search. But before that, do you guys have any questions about like dynamic programming or greedy that? You can feel free to also email me, but it's better if you have any like quick things that you want to clarify. Yeah. Did you? Yeah.
So just in general, it seems like greedy algorithms are optimal if there's only 1 degree of freedom in the solution, whereas if there's more than one, then you need dynamic programming. Is that true in general?
It's a decent heuristic, but it's not generally true. I mean, it could be that even when you have multiple things, there's a way of combining these two. So you're right, you could think of it as like essentially one objective, right? So like a nice example of this would be, so you have jobs with a certain completion time and a certain cost. Okay, so like this example that we saw, some processing time and a cost. Okay. And maybe you have a weighted sum of these completion times, where the weight is the cost. Okay. So yeah, so even that could be done by greedy, turns out. Okay. So, but there you compute this ratio and you sort by the ratios. But essentially you're right, you reduce it to one parameter thing, and yeah. So, but dynamic programming is usually much more general, but it has its disadvantages, that it's usually slower, and it's also I mean, often it requires a lot of memory and so forth, which greedy algorithms don't. Okay, so that's why greedy things are preferable if they work. Okay, so any other questions? Okay, so let's move on to this thing, which is people don't usually do in algorithms courses, but I think it's very important to know. Okay, so this is this notion of local search. Okay. So what is local search? So far we've been trying to build solutions carefully, right? So like in greedy algorithm, you start off with an empty solution, you build one by picking the best thing at every step. So what local search tries to do is, you start off with a full solution, okay? Start off with an arbitrary full solution, and you try to improve it, okay? So this is what one does in life for many things, right? So you start out with something and then slowly tweak it over time. And it turns out algorithms that you develop like this are often quite good. Okay, so let's see some examples of this. Okay, so you start with some reasonable solution, and then you try to improve. And if you can't improve anymore, you stop. Okay? So if you can't improve anymore, you stop.
And the solution is selected randomly?
The starting one, you mean? The starting one, for now I'm assuming it's arbitrary, but yeah, you could pick one at random too. Yeah.
Is it possible that the amount of improvement that can be made is different based on your starting solution? So like, if you start with one solution, improve as much as you can, it might not be as good as if you had started with a different solution and improved.
Yes. So this is a common thing. So when you have, we'll see some examples of this. When you have multiple local minimum.
It's a numerical approximation.
Yeah, we'll just see some examples of such things. Okay. So if you cannot improve anymore, you stop. Okay, so let's look at a very simple example to start with. Okay, so let's say you have a grid. Okay, so a grid is just think of this as some finite domain. Okay, so this is the origin. Yes, can you see this? Yeah, okay. You can see this as well as I can, so maybe it's fine. And then you have, I don't know what this is. This may be like 6, 6 or some point like this, and you have this grid like this. Okay? And you have this function that you want to minimize. And I want you to find a point in this grid, okay, so something over here, which minimizes this function f. So this is the kind of things for which local search actually works really well. Okay, so you have some function, and you might want to optimize this. Okay, so you want to find the minimum of this or the maximum of this or something. So what you can think of doing is this very simple algorithm, right? So you start off somewhere, okay, and you try to move left, right, top, down. Okay, so you go and try going in each of these directions. See if your value of f improves. Okay, and if so, you just go there. Okay, so maybe going here will improve this. Okay? And next time maybe you want to go here to this or something like this, and so forth. And maybe eventually you'll come to a point where you can't improve anymore, which means that the 4 squares to the right, 4 endpoints to the right, right, left, and so on, are all worse than this. Okay, so you stop when f of xy is actually smaller than f of some x plus 1 y, and these 4 numbers.
Isn't it like greedy only because we are at a step when we have this value of the f reducing, so we feel like okay, this is the optimal one, then we move again. So it's
in the same spirit as greedy, but usually in greedy algorithms you try to you try to grow a solution. Okay, so like we did in this kind of interval building thing, right? So you say that okay, I pick one, then I pick the next one which is as good as possible, and so on. So that doesn't quite make sense in this kind of a context, because maybe it does if you say okay, I'm going to pick a good x first, and then I'm going to pick a good y first, and then stop. Okay. While with local search, what you do is I pick some x, pick some y, and then say that oh okay, now maybe I can change x and improve in x and so on. Okay, so that's the spirit of local search, where you build something and then you try to see if you can tweak it. And you keep doing this until you cannot improve anymore. Okay. Greedy is usually a one-shot thing. Okay, so you may keep making decisions and then you end. But you're right, there is a close connection between these two, and often one works when the other does. Okay, so yeah. Actually it's the other way around. So usually whenever greedy works, some form of local search will also work. Okay, so yeah. So other questions? Okay, so it turns out that this is actually a powerful approach. Okay, so this is what is called coordinate descent. Okay, and it's also related to what's called gradient descent. Okay, so in gradient descent, you don't necessarily move to just its neighbor. You could move to something that's along a different direction. Okay, so in that sense, it's a little bit more general. But if you just restrict to moving along the axis, it's what's called coordinate descent. Okay. So this is a very powerful numeric tool. Okay, so it's a very powerful numeric tool. And for many, the nice thing about this is you don't need to know f in like a nice closed form even, right? So you just need to be able to evaluate it at any given point. Okay. So that's the nice thing about it. Okay. And yeah, so the other example I want to give is, this is something we'll see maybe in like a month from now or something like this. So this is called linear programming. Okay, so it's So how many of you have seen linear programming in some form? Okay, so some of you have. So basically what it is you have some feasible set of points, okay? And this feasible set of points is just given by, you can think of it as a polytope, okay? So you can think of it as like something that looks like this, where every face is a plane, okay? And you have this body that's generated by the intersection of such half spaces. Okay, so you have each plane defines some half space, and the intersection of these things forms a polytope. What's called a polytope. Okay, so we'll define these things in a bit. When we do this. But so linear programming is basically you have an object of this kind. For now, let's just call it k. Okay, so this is just some polytope, and you want to maximize a linear function over this polytope. Okay, so you want to maximize C transpose x subject to x being in this K. Okay, so think of C as a n-dimensional vector. So everything, all this action is happening is in n dimensions. Okay, so this figure n is 3. And C transpose x is basically a linear function, which basically means C1 x1 plus C2 x2 plus so on up to Cn xn. Okay. x1, x2 up to xn are the coordinates. Okay. And you want basically this point x1, x2 up to xn to belong to this polytope. Okay. So that's when, so this is what is called linear programming. Okay, so you have a polytope that's defined by these things, and you want to maximize it. So it turns out that there is this very famous algorithm called the simplex algorithm. Okay, so the way it works is exactly local search. Okay, so what it does is, so you start off at some corner point, okay, and then you move to a neighboring corner that that could increase the value of this objective. Okay, so at each step you kind of look at all these directions. Okay, so maybe you could move here, you could move here, you could move here, and so on, and you just move along these edges. Okay, and you stop when you can't improve your objective anymore. Okay, so that's yes. So this is called the simplex algorithm. So it turns out this is very useful in a whole bunch of This is one of the most commonly used algorithms in practice for solving these things. Okay, so we'll get to that in a bit. And I just want to say that this is a natural example of
Local search.
of local search. Yeah. So okay. So let me start. Let me just do a quick overview. So one thing I want to say, which I guess I already said, is that it often works a little bit better than greedy. So it works reasonably for many problems. And some examples include like clustering problems and these kind of numeric optimization problems and so on. Okay. So for clustering data points also this works quite well. So you want to find points that are close to each other. Right? So you start with some clustering which is okay, it's not too bad. Then move points to clusters where it's actually closer. Okay, so you notice that this point is closer to other points in this current cluster. Okay, so you move this point there. Okay, and then you get a new clustering. Okay, and you continue doing this. Okay, so you can keep improving clustering. These kind of things tend to work. And it's actually used really frequently in practice because you often come up with some solution by using some heuristic. Often you do some greedy or some heuristic and then you try to improve this solution. Okay. And so this again, it has the same issue as with greedy, just that it's often tricky to prove guarantees. It could be. So even for problems like this, it took a while for people to come up with proofs that they are good. Okay, so I want to do a very simple example today. Okay, so today is going to be the scheduling day. Okay, so this is again going to be a scheduling example. Okay, but this time it's a little bit different. Okay, so it's different in two ways. Firstly, you have a bunch of processors. Okay, so let's say you have M machines. And as before, you have these jobs. So you have J1, J2 up to Jn. This guy has processing time P1, P2 up to Pn. Okay. And what you want to do is, it's actually the objective that someone mentioned here, which is that you want to assign each job to some machine. Okay, so you have M machines like this, all of which can process the jobs. And maybe this guy you want to associate. There are M machines like this. And A1, A2 up to AM. And I want to assign each job J to some machine AI. Okay? So let's say this one goes to some. And what's the objective? Objective is to, okay, so actually let's just look at the running times. Okay, so let's say this machine A1 gets a bunch of jobs. Okay, so it gets let's say J1, which runs for time P1, then it gets J8 or something which has P8, and so on, and this ends at some time. So this machine completes at a certain time. So it has this finish time. Okay, so let's call this F1. So also machine 2 can have, it gets assigned a few other jobs and has some F2 and so on. And the goal of this problem is to do some form of load balancing. Okay, so which means that you don't want any machine to get assigned a very big Fi. Okay. So the objective is to minimize the max of these Fi's. Okay, max over I. Okay, so is the problem clear? So you want to have these bunch of jobs. You want to group them into M pieces so that there's some kind of load balancing. Okay, so this is the problem. And how would you go about doing this?
So all machines are equal in the sense that
Yes, all machines can take the same time to process the job. So that's a good twist. So you can think of local search even otherwise. Okay. So you can think of various ways, right? So one way could be you go through the jobs and then you try to, maybe you want to go through the jobs and then try to assign one to the machine that's least occupied. Okay. So this is a natural heuristic. So it is assign a job to the least occupied. Machine. Okay, and keep doing it. So it turns out this is actually a decent heuristic. Okay, but I want to actually do a local search algorithm, which is even simpler. Okay, so the local search algorithm basically does the following. So you start with any assignment. Okay, so you have some assignment. Okay, so which ends up with E1, E2, these are the machines, AM, each one gets some jobs. And what is a local search, what would a step in local search look like? So you have this solution, you want to see if there's a better solution, right? So, and remember the goal is to minimize max over I of this finished. Okay. So if you want to reduce this max over I Fi, so what's the machine whose load you have to minimize? Yeah, the most loaded guy, right? So maybe there are more than one of them, but at least one. You have to reduce that quantity. So maybe what you want to do is, okay, so I look at the most loaded machine and I try to move one of the jobs that's assigned to it to a different machine. Okay. And if this maximum reduces in this process, then I do it. Okay. And if there's no such move possible, then I just say, oh, okay, this is the best I can do. Okay. So it's an actual local search algorithm. So try to reduce load on the most loaded machine. And stop if it's not possible. And you just return that solution if you can't do these updates. So, okay.
Do you pick it randomly from the?
No, try everything. Okay. So what I mean is, you have this most loaded machine. Let's say it's A2. Try to see if you can move. Try to see if you can move this job somewhere else, or if you can move this job somewhere else, so on. Okay, so you actually have to do a bunch of work. So yeah.
Are you always wanting to move the job to the least loaded machine, or is that not necessary?
It helps the most if you do it, right? Because that's the best you can do in some sense. Yeah.
There are multiple possible moves. Which one you?
Yeah. So as you were saying, so this algorithm doesn't care. Okay, so the number of iterations will depend on some bad choices. Like you don't want to move to a machine where you only very slightly improve this objective value, right? So you would want to move to a place where you improve this objective value by a reasonable amount. Okay, so otherwise, you make some progress, but you don't gain too much. But for this algorithm, we don't care. Okay, so that's one thing about local search, which is you just try to make some improvement. Okay. So how much improvement you make will determine the running time of these kind of algorithms. Okay, so if you make only very little improvement, then maybe it wasn't worth doing this step. Okay. So that will come to later, but that's for now it doesn't matter. Okay? So as long as it's possible to reduce the load, do it. Okay? Yeah. So just the succinct answer is pick any move that can do this. Yeah. Okay. So good. So this algorithm. Yeah.
The input is an already existing solution and you want to.
Yes. So I mean, you start off to any assignment. You don't care. Just maybe you put everything on one machine.
Okay.
And then you just try making moves like this.
So algorithm starts from there. So
Yes.
we have done some random assignments.
Yeah. By the way, one thing that all of you should remember is the difference between random and arbitrary. Okay. So random usually, when in theory when we say it, it means uniformly random or coming from some distribution. Arbitrary means anything possible. Okay. So people often tend to use one for the other. Yeah. So all right. So this is the algorithm. And the theorem is the following. Okay, so I don't know if you can see it, but the theorem is the schedule that you produce like this. So this algorithm will run for some time and stop, right? And the final schedule, whenever you stop, okay, is at most twice as long as the optimal schedule. Okay, which means for this objective, the optimum schedule will have some value opt, right? And we are saying that if local search stops, okay, then the value of the objective is at most 2 times opt. So it's not too bad. Okay, so it's the same kind of thing that we saw last time. Okay. So this is the theorem. Yeah. We have 1 minute to prove it. Okay, so let's see. So maybe we'll do this next time. Okay, so but it's a natural thing to think about. Okay, so you start with what happens when you cannot move, okay, and then you reason about it.
The lecture goes till 12:05.
Oh, it goes to 12:05. Oh, okay, then we have ample time. Okay, so okay, so let's do the proof of this. And this is how you generally analyze local search, where you say, why does the algorithm stop? Okay, so you say that we said that it ends when there's no other improvement possible, right? So what does it mean to say there is no other improvement? What does it mean to say there is no improvement?
That alpha phi is less than alpha phi minus 1 and less than alpha phi plus 1.
Yeah, so if you look at basically not just I plus 1, right? You can move to any machine. So okay. So let's look at the most congested machine. Okay, so let's call this. Let's assume without loss of generality this is A1. Okay. So this has a bunch of jobs. What we are trying to do is move one of these jobs to a different machine. Okay. And we are saying that doesn't improve this objective. Okay. So remember the objective was max over I of Fi. We are saying that, so what does this mean, right? So suppose I try to move a job of length P to a machine, to some machine Aj. And this is not improving the time. So what should Fj be?
It's not smaller than the P.
Greater than Fj minus P.
Yeah, it has to be bigger than equal to F1 minus P, right? Because this was F1. If Fj was strictly smaller than F1 minus P, then moving this here would actually help you. Okay? So, so this is one thing we have, right? So if we can't move a job of size p here, then we have this guarantee that fj is bigger than or equal to f1 minus p. Okay. So now I want to claim that, okay, so firstly, can p be very big? Okay, so if I look at f1, if I look at this machine A1, look at all the jobs it got. What happens if it had gotten just one very big job? Yeah, then the optimum has to be at least this big, right? So if, so there's like two cases. Case 1. If A1 got only one job, then the schedule is optimal. The schedule that you produce is optimal. So it means it must have at least two jobs. Okay? Which means that at least one of them has to be smaller than f1 by 2. Okay? So case 2 is greater than or equal to 2 jobs, which means that at least one of the jobs is less than f1 by 2, okay, less than or equal to f1 by 2. Okay. And this is nice, right? So what this is saying is, so I can try to move this job to some other machine. And if that's not possible, I get that fj is bigger than f1 minus p. Okay, and I know p is smaller than equal to f1 by 2. So in particular, these two observations tell you that for all j not equal to 1, you have fj is, actually it's by definition true for j equal to 1, but fj is bigger than equal to f1 by 2. Okay? Because we know that A1 had at least two jobs, at least one of them was smaller than or equal to f1 by 2. And if that guy could not be moved to one of these machines, then it means that each of these guys is bigger than or equal to f1 by 2. So that's easy. Okay? And so now I want to claim that opt has to be bigger than or equal to f1 by 2. Okay? And why is that? So what this is saying is that every other machine is at least occupied until f1 by 2, right? So it's at least f1 by 2, this is at least f1 by 2, and so on. Okay? And none of them had any free space in between, right? So the total weight of the jobs is at least f1 by 2 times m. Okay? So there is no way there can be a schedule where every machine gets smaller than f1 by 2. Okay? Because that would contradict the fact that means that the total sum of the processing times is strictly smaller than f1 times m by 2. Okay? So that's the argument. Okay? So this implies that because otherwise total weight of jobs or total processing time is less than f1 by 2 times m, and that's a contradiction, right? Because by definition we said that it's f1 by 2 times m minus 1 plus f1. Okay, so it's a little bit even better than that. So yeah.
So if we have freedom in assigning the jobs,
yeah.
Say if we order the jobs and assign them to various machines in terms of considering completion times.
Okay. Yeah.
This can be much more optimal.
This could be better, but you can come up with examples where there's also two-factor ones. So the same factor as this. So yeah. So in fact, so this is a two-factor of the optimum. Turns out there is a slightly nicer algorithm that does 4/3, okay, and that's the best one can do. Okay, so, but this is a very simple algorithm that gives a two-factor.